Okay, so let's start our class. We're in the final part of 4.3, but before we make the jump to the next subsection, there is one last topic that we must talk about, which is logarithmic differentiation. And in a nutshell, it's just a useful technique in case you have a complicated function where you have products or quotients, and by using the properties of the logs, you can get a simpler computation for the derivative. So before we illustrate the technique with an example, we'll just say what it's related to. So taking the derivative of a function that involves either products, quotients, or powers can often be simplified by first taking the logarithm of the function. And so this is what the logarithmic differentiation technique is about. That's pretty much it. So I think it's better to just make an example so you understand why we're doing this. It's essentially, look, for products, quotients, or powers, you have log rules which simplify. The log of a product is the sum of the logs, etc., etc. And you make your life easier by just converting to the log and getting simpler operations. So the example is related to the derivative of the function f of x equal cubic root of x plus 1 divided by 1 minus 3x to the fourth power. Right? So far, so good. And in the solution of the problem, we're going to indicate the steps one by one. So the first step is to take logarithms of both sides of the equation. Or the expression for f if you want. And then we will use the quotient and power rules for logs. Okay, so let's proceed, right? So we have this function. If I take the log, again, I have a quotient, so this would be the log of the difference. So the log of the numerator, which is cubic root of x plus 1, minus the log of the denominator, which is 1 minus 3x to the fourth power. Sure. So I can still further use the properties of the logs, as you remember, because this is a cubic root, so the exponent of this expression, of the argument, inside is 1/3. So this would be the same as if I write 1/3 of the natural log of x plus 1. And then again, I also use the properties of the logs, so the exponent comes down, 4 times log of 1 minus 3x. So far so good, right? I have not even taken the derivative. I've just taken the log of the function, because I will get a simpler expression when I take the log, the derivative of the log. So at this point it's just log properties, but then we will see how the derivative of f comes up. And it comes because of the chain rule. So now we use the chain rule logarithms. To differentiate both sides of this equation. And then we get the following. So on one hand, okay, we have this expression, right? Let's say I take the derivative with respect to x of this function, natural log of f. On one hand, if I apply the chain rule for this, I would have, okay, the function as the denominator, and then multiply it by the derivative of this object, right? So far, so good? Okay. Now, the nice thing is when I apply to the derivative to the other side, right? Because then I know the formula. So this is 1/3. The derivative of natural log of x plus 1 is 1 over x plus 1. And then minus 4. And again, the technique for the derivatives of the logs, right? So I have the function as the denominator, and then the derivative of 1 minus 3x, so minus 3. So far, so good? I'm just using properties of the derivatives of the log. And if I simplify this, I have 1 over 3 times x plus 1 plus 12 divided by 1 minus 3x, right? So you start to see why we did this. I mean, if I took directly the derivative of f, I would have a quotient, which is a little bit involved. Here I have two summands, which I actually simplified with the properties of the logs. And life is good. It's getting pretty simple. And in fact, I can pass f to the other side. So I would have f prime of x equal. So f of x times 1 over 3 times x plus 1 plus 12 divided by 1 minus 3x. So one last step that I could do is to simply plug in the formula for f that I had over here, and I would finalize the calculation. So it's much simpler when you have all these products or quotients or powers to just apply the log and then take the derivative, and then by the chain rule, just get a simpler expression. So the final part of this exercise is simply to plug in what f was, which is cubic root of x plus 1 divided by 1 minus 3x to the 4th power, and then multiply by this expression, 1 over 3x plus 1, of course, with the 3 multiplying the whole x plus 1, times 12 divided by 1 minus 3. Okay? So clearly there is an efficiency in this calculation. It's much simpler to do than actually deal with the whole quotient. Of course, it depends if you have that kind of function that involves several products or quotients or powers. It might be useful at some point, and a particular example, you could say, is, well, logs of these quantities are related to a relative difference, and that's what we will see in the next example. But before we continue, is the procedure clear for everybody? Yeah? You guys saw what we did? We had a complicated function. We took the log. We used the properties of the logs to make it simpler. We took the derivative of the log. Then I have f prime over f, because that's by definition the derivative of log of f. And by plugging in back f, I did the computation in a simple fashion. That's all what I did. So the next comment is that if I have a function q of x, which is differentiable, let's say that I consider the following object, right? So let's say that I consider the derivative with respect to x of natural log of q. So the same way we did this example, what we would have is the function q in the denominator, and then the derivative of q, right? So q prime of x divided by q of x, in the notation that you are more familiar with. So, does this ring a bell, or does this sound or look familiar to anybody? What is q prime over q? What do you think it is? I'm taking the rate of change of q divided by q, right? So I'm comparing the rate of change to the original quantity. This is like, in a way, like a relative change, because I'm dividing this derivative by the object by itself. So the ratio that we have here is the relative change of q of x. You see? Because I'm measuring the change with the derivative, but I'm dividing by q. So, I mean, you can think about it in many ways. With the division by q, I'm kind of like taking out the units of q. It's also comparing the change with respect to the value of q. So, of course, that makes more sense because it gives like some non-dimensional with respect to q at least. And what we have is that the relative change of a quantity q of x can be computed by finding the derivative of natural log of q, right? So what this is saying is that if I take the derivative of natural log of q, I have the relative change of this object. Where I compare the change to the actual quantity, that's why it's relative. This will pop up later. There are many things to comment. In one of the examples related to applications, we'll see something again along these lines. And when we briefly study differential equations, we will see how this kind of object comes up. So just wait a little bit. I think for the moment, it's kind of like intuitive that this is measuring a relative change. We will do some specific examples related to this quantity later on. So, well, the final comment related to this, tying it with logarithmic differentiation, is that logarithmic differentiation can simplify the computation of growth rates. Which again, go back to this expression and try to think about it a little bit, especially if you're not familiar with the concept of relative change, relative difference, etc. But in any case, I mean, as far as we are concerned with the logarithmic differentiation, this is what we would need. And now we will start a new subsection, which is related to additional applications. And, well, who has used a Gaussian distribution before? Or a Gaussian curve? A normal distribution? Okay. So one of the examples that we will see will be related to that. So it's actually pretty useful, and it comes up for all the people who do certain kind of statistics. So that will be the second example that we will do. But before, let's just start into the section, which is 4.4, additional applications, which, for example, exponential models could be one. So, of course, there are different examples. This is actually, beyond the particular case of the exponential. Part of the reason to take a calculus course is because the concept of derivative is very geometrical. And with the information of the derivative, you have an idea of how the function behaves if it has a derivative, because you can know where the function is increasing, decreasing, etc. So part of the skills that you are supposed to have after you learn these concepts of derivative is how to sketch a curve given that you have the information of the derivative. So the first application is in curve sketching, where the general instruction is of some sorts is this. You first use the derivative to find intervals of increase and decrease. And the second indication is to use the second derivative, f double prime of x. Who has seen f double prime? People, right? To determine the concavity. So basically, how is the derivative growing? So you consider the rate of change of the derivative, which is the second derivative. So the particular example that we will use is 4.4.1, which indicates to sketch the logarithmic curve, in particular the graph of the function f of x equal to x squared minus x natural log of x. So we just have to do the plot of this function, given that we know our formulas for the derivative. So the solution, again, in different steps. The first thing to notice is that you have the natural log. So this is only defined as a whole for the function f for x greater than 0. So f of x is defined only for x greater than 0, because I got the log. Then, if I compute the derivative, f prime of x, the first term is 2x, and then I have minus 8 over x. If I want to put the terms together, so I would have 2x squared minus 8 divided by x. Right? So far, so good? So I just added these two. Sorry. Can everybody see? Yeah. Okay, so why am I doing this? Because, okay, in general, besides this function, which are the regions where the function is increasing if you know the derivative? What is the condition of the derivative? The derivative should be positive or negative? Do you guys know this? Or no? Well, it doesn't matter. We will start doing it. So the idea is that if the function is increasing and it's differentiable, f prime is greater than 0. If it's decreasing, f prime is negative. And then possible critical points are found by finding f prime equal to 0, which is what we will do. So if I want to find a critical point, which is the definition of critical point is that f prime is equal to 0, this has to be 2x squared minus 8 over x equal to 0. However, on one hand, we know that x has to be positive because the log is part of the arguments. So the only way that this can be 0 is if 2x squared is equal to 8. So that this factor is 0. That is clear, right? So if I simplify, well, basically I would have x squared equal to 4, which means that x is equal to 2 because I have the condition x greater than 0 from here. So there is no way that I can consider the other root. So just pass x squared equal to 8 divided by 2, which is 4. Take the square root. X has to be positive. You have that. So Well, the other thing, of course, look, there are many indications, especially in first calculus course, on how to test the sign of f. Of course, there are many ways. The simplest way, like the baby method that they may have even taught you in high school, is to find the critical points, then to find the value of the function between those critical points and see if it's positive, negative, etc. A more refined way is to actually, by inequalities, just deduce which are the regions where the derivative is positive or negative. So, which is what we will do, because in this case it's simple enough to do it that way. So what we will do is that we will test the sign of f prime of x. Well, we know that x has to be greater than 0. We know that x equal to 2 is a critical point, because f prime of x is equal to 0 at x equal to 2. So we will test in the following intervals. For the interval from 0 to 2, and for the values of x greater than 2. So this is just by inequalities, where I can do the following analysis. If x is greater than 0 but less than 2, that means the x squared is greater than 0 but less than 4, which means that 2x squared is greater than 0 but less than 8, which means that 2x squared minus 8 is less than 0 for this condition. This is just an inequality way to derive this. Now, why this is useful? Because f prime is equal to 2x squared minus 8 divided by x. I know that my problems are such that x is greater than 0, so this factor in the denominator is always positive. Therefore, this one defines the sign of f prime. That's why I'm, like, just by inequalities deducing this. Is it clear? It's pretty logical. So, in that case, 0 between x and 2 implies that f prime of x, which is equal to 2x squared minus 8 divided by x, where I know that x is positive, is negative because of this. Right? And just by inequalities, I proved it. I don't have to test in little points like in 1, etc., etc. Usually this is the more general way in which you can do it. Of course, it depends on the function is easy enough. Maybe there are some cases in which the function is very hard to manipulate, I don't know. But in this case, it's simple and we can do it. In the other case, which is x greater than 2, that means that x squared is greater than 4, which means that 2x squared is greater than 8, which means that 2x squared minus 8 is greater than 0. And now we have again this factor that we were caring about, which we can simply, by implication, just deduce that for the case of x greater than 2, we have that f prime of x, which is equal to 2x squared minus 8 divided by x, it has to be positive. Right? So we proved that for this interval from 0 to 2, the derivative is negative, which means that the function is increasing or decreasing. Have you guys seen this before? How the sign of the derivative determines increase or decrease? No? Well, just think about it. The derivative is the slope, right? So if this helps you, I have a function, I have a plot. Let's say that the derivative is positive. That means that the slope of the tangent line goes like this, right? Because the derivative is positive, right? So that means that the function is increasing as I increase in x. If on the other hand, I have this stuff, then that means that the function is decreasing. This would be a negative derivative, I have the decrease. If you have not seen it, this is the geometrical criteria. And of course, the derivative is something like this, you know? Like maybe, well, if you want. So this is the function, this is the derivative. So, if you have not seen it, this is very important. This is an important criteria. It has, of course, a lot of geometrical intuition. But now, the important thing is that we have determined what are the signs of f prime. So if I make a little plot, well, I know that x is greater than 0. Important point, 0 is not contained in the domain of the function. 2 is a critical point. Then the function is defined for all values of x greater than 0. I know that the derivative, if you remember, for x between 0 and 2, f prime is negative, right? So if I consider the sign of f prime, this is negative, so I have minus. Now if I consider the values of x greater than 2, f prime is positive, so the sign of f prime is positive. So again, that means, by this geometrical argumentation, so this is a case if you want f prime greater than 0, this is a case f prime less than 0. So in this case, you have that the function f is decreasing, and for this region, you have that f is increasing, right? So if I were to make an adventurous guess on how the plot looks like, well, here it decreases, here it increases. And so you can see how we will have a minimum in this case, right? The function is decreasing over here, and then it's increasing over here. It has to do something like that. So clearly the minimum is at the critical point. That is the reason for which we study always like these critical points of f prime equal to 0, because there are potential points in which you might have or might not either a minimum or a maximum, or etc. So here it's decreasing, here it's increasing. Here you have the minimum. If you look for the name of that proof, where basically the function is decreasing here and increasing here, then you must have a minima that is called Fermat's theorem. Okay? But that is the reason for which we look. I mean, if you think about it here, if you want me to write it, this is f prime less than 0, this is f prime greater than 0. The point 2 is precisely where f prime is equal to 0. Oh, sorry. F prime greater than 0. F prime at 2 is equal to 0. And so we know that we have a minima here. So, of course, local. So there is a relative minimum, meaning a local minimum, at x equal 2. Then if I have f of 2 equal to 2 squared minus 8 natural log of 2, so I'm evaluating the function of 2, I have approximately minus 1.5. So there is a local minimum point at 2 minus 1.5. So if you want to is a relative minimum. But you see why it was of interest to find the sign of f prime? Because I can find the functions or the regions where the function is decreasing, where it is increasing, then deduce geometrically that I have a minima. Of course, there are some other criteria to actually determine it, but this is pretty intuitive. I also need, in order to evaluate the concavity, the second derivative. Because, well, I will give the explanation in a second. So first, let's do the computation. If I compute second derivative, f double prime, well, remember what was f prime, so it's this. It's actually easier to go over here. So f double prime is equal to 2 plus 8 over x squared. Right? Just remember what f prime was. Take again the derivative. The first one you get 2, the second one you get plus 8 divided by x squared. And I think you guys notice that this is a positive quantity. Right? You have x squared. So this is positive for all values of x greater than 0. Well, in fact, in general, but just to give an explanation of why we care about the second derivative is, well, if you think about it, what we have done, f double prime is equal to f prime prime, which is greater than 0. And since f prime is an increasing function, the graph of f of x is always concave up, meaning that you don't have inflection points. But what do we mean to say? Think about it. We have f double prime, which is f prime prime, right? So you're taking the derivative of f prime, so that means you're studying the behavior of the derivative of the function. And if f prime prime is greater than 0, it means that the derivative is always growing, right? So it's increasing. So let's say that this is your initial slope, your initial derivative. You travel through x, it is becoming higher and higher. So clearly there's a concavity sense. That's why it's concave, right? If I think of the slope, if it's growing as I travel through x and making it greater, clearly you have some concavity. That's why we care about this criteria of the second derivative. Now we have more information, of course. All this is with the aim to draw the graph, but we have to do certain analysis. And the next piece of information that we will study are possible asymptotes of the curve. So, okay. Regarding asymptotes, we can show that if I consider the limit as I approach 0, of course, with numbers greater than 0, of the original function f, x squared minus x natural log of x. What would this be, actually? Okay, so you're approaching 0. Does x squared have an issue? No, it goes to 0, right? So the issue is with the log. What happens when I approach log of x? What is the limit if I just consider the limit as I approach 0 of natural log of x? Goes to minus infinity, right? You guys remember? When we draw the graphic. Here you have a minus sign though. So instead of going to minus infinity, you go to plus infinity. Now, if I consider the other limit, when I go to plus infinity of this, x squared minus 8 natural log of x, well, here it would seem that you would have a competition between this term, which is pretty big, minus this other term, which is also big. This is actually related to the difference in which the, think about it, the exponential and the log are inverse functions, and you know that the exponential grows much faster than x. So this actually means that for the log, it grows much slower than any polynomial. And therefore, this is the term that would win. I'm not giving like a super detailed proof of this, but essentially the whole idea is that the polynomial grows much faster than the log. This is why the positive term wins, and that's why you have plus infinity. So in any case, the actual piece of information that is useful is this one, because as I approach 0, as x approaches 0, meaning that you approach the y-axis, what you have is a vertical asymptote. Think about it, right? I have the axis, I approach 0, it goes to infinity. It's doing it. That's why the y-axis is an asymptote. So this other piece of information means that, well, we were not able to find an asymptote regarding the x-axis. So we have no horizontal asymptote. And the last piece of info is to look for the intersections with the x-axis, which are called X-Intercepts. So we have to solve the equation f of x equal to 0. So x squared minus 8 natural log of x equal to 0. You can pass to the other side. So x squared equal to 8 natural log of x. You could even do some simplifications. So just to give you an idea, at the end you would have to do it numerically, either with a computer or your calculator. But, well, you would have something like x squared over 4 equal to 2 natural log of x, which you could actually express like x over 2 squared natural log of x squared if you want. But in any case, just to provide you the solutions of this, regardless of the method you use to solve it. It's x around 1.2 or x around 2.9. This is just an important piece of information in order to draw the plot, which will be now our objective. And in the plot, we will join all the info that we have, right? So this is the y-axis, this is the x-axis. We're going to plot the function f of x equal x squared minus 8 natural log of x. If you remember, when I approach 0, I go to infinity, right? Actually, maybe it would be useful to present the other piece of information that I had before. If you remember, right? So this is the region where the function is decreasing from 0 to 2. After 2, the function is increasing. We know that we have a local minimum over here, which is actually going to be the global minima. We also know the concavity, so the function is always concave up. We know that it tends to plus infinity on this side. And we know that the intersections with the x-axis are basically 1.2, so this is one intersection. Then we have the minima at 2. Then we have the other intersection at 2.9 almost. And, well, we have something like this, right? So this is matching two pieces of information. That the function is decreasing in this region, and also that the limit as x approaches 0 of this function is plus infinity. That's why the y-axis is an asymptote. Okay? Is this okay?
Yeah.
Okay. So here you have the asymptote, the y-axis. The function is decreasing. It crosses the x-axis at x equal to 1.2. It will have the minima at 2. It will do something like this. Then the function becomes increasing. It's still concave up. This is the other piece of intersection at 2.9. And then it goes to infinity, right? I mean, it's not a beautiful plot, I must admit. It looks pretty crappy, but at least it gives the idea of the information. So the minimum point is 2 minus 1.5. If you were to evaluate the value of the function at 2, this is the function f of x equal to x squared minus 8 natural log of x, where you have the asymptote. It grows to infinity, the intersection points, the concavity, where it's decreasing, where it's increasing, and the minimum point. So we're using all the information that we have from the function f prime, and f double prime in order to make a plot of the figure. Okay? So this is the technique. Look at the function, find the derivative, study the sign of the derivative to find the regions where it is increasing or decreasing. To study the second derivative, to study the concavity. Maybe you can figure out some local minima. Potential candidates are the critical points. If the function is, if it's clear enough for that function that you might have an asymptote, you do the study, which is what we did in this case. And then it might be helpful to find intersections just for the plot, right? But it was very systematic. And I mean, just the last observation, okay, the shape is concave up. And the second piece of information is that the y-axis is equal to 0 is a vertical asymptote. Okay. So, in the last 10 minutes, we will start the example related to the Gaussian curve or the exponential, basically the Gaussian distribution. We won't finish it, it's okay. We have 2 days to delve on applications, so this is not an issue. But it's good to start bringing up the conversation. So what we will do now is to sketch an exponential curve. And the actual command of the exercise is the following. Determine where the function f of x equal to e2 minus x squared divided by 2 divided by square root of 2 pi. Who has seen this function before? Does this look like a normal distribution, or does it ring a bell on what a Gaussian is if you have done a fit or not? No? Well, so you have to determine for this function where it is increasing and where it is decreasing. And where its graph is concave up, and the other region in which it is concave down. Then you have to find the relative extrema, inflection points, and draw the graph. So you probably have seen this before, but what is a condition to have an inflection point? You guys remember that at least it's related to the second derivative? Is that common knowledge? Okay. So, well, the first step is to compute the derivative. If you have not seen, this is a normal distribution, has several names, a Gaussian, bell-shaped curve, etc., etc. It's very famous. If we take the derivative, well, we have minus x e to the minus x squared over 2, because when you take the derivative of x squared, there is a factor of 2 that cancels out. That's why it's not appearing. But you still have the constant in the denominator, the square root of 2 pi. And what you know is that since the exponential, e minus x squared over 2, is always positive, if you want to find the points for which the derivative is 0, f prime equal to 0, that happens if and only if x equal to 0. Has anybody seen this sign before? This double arrow? So if you have not seen it, this means if and only if. Okay? So the only point where this can vanish, of course, is when x is equal to 0. So that is our only critical point and potential candidate for either a local maximum or minimum. And if I evaluate the function at that point, of course, then I have e of 0 divided by square root of 2 pi, so 1 over square root of 2 pi, which is almost 0.4. So the only critical point is x equal to 0, y equal approximately 0.4. Okay, so little by little we're understanding more about this problem. What would be the next step, actually, given that we did a similar approach in the previous exercise? What should I do now? Sure, that's true. That's an important step. I also have to analyze the signs of f prime, right? To find the regions where it is increasing or decreasing. We will do that. Just first we have to, well, I mean, maybe I will do that after, but it's kind of clear, right? Because, okay, the exponential is always positive, and here you have as factor minus x. So for x negative, minus x is positive, so the derivative is going to be positive for x less than 0. And for x positive, for x greater than 0, the derivative is going to be negative. So we have kind of like something similar to what happened before. I will do the plot later on, but just, I mean, in this case, the function is simple enough to analyze. That's all my point. If I compute now the second derivative, precisely to study all this concave up, concave down stuff, Well, I have first the derivative, so minus e minus x squared over 2 divided by square root of 2 pi. And then I have, again, the factor of minus x twice, of e minus x squared over 2 divided by square root of 2 pi. So if I were to factorize, this is x squared minus 1. The common factor is e minus x squared over 2 divided by square root of 2 pi. But do you guys see why I have the minus x squared? Because I have I have a product. The first one is easy to take the derivative. The second one, I have the same factor again, so that's why it's squared. And then if I put it in a nice fashion, I have this stuff. So if I were to find points where the second derivative vanishes, now it's clear, well, this factor is always positive, so the only possible consequence is that x squared is equal to 1. And then that means that x is equal to plus minus 1. Is the approach clear at this point? I did the computation, I factorized. The only way this can be 0 is if this factor is 0, because this one is always positive. So x squared, is there a question? So because x squared minus 1 has to be 0 in order for the second derivative to be 0, that means that x has to be either plus 1 or minus 1. Now, I will keep collecting information. Wait, is there a question of this, or is the procedure clear? Because I noticed some agitation in the group. Right, because the inflection points happen where f double prime is equal to 0. That is the main reason. So I'm trying to collect as much information as possible. So if I find the point where the second derivative is 0, it's a possible inflection point. It's a potential inflection point. And then what I want to do is to evaluate the values of the function. So f of 1, if I evaluate in the original function, I would have e to the minus 1/2 divided by square root of 2 pi, which is around 0.24. If I do the computation of f, not of f double prime, but of f of minus 1, I actually get the same value, because remember that the exponential depends on x squared. So this is e minus 1/2 divided by square root of 2 pi, which is, just to emphasize, this is f of 1, which is around 0.24. And again, this is the condition. If you have not seen it, I was assuming that people had seen this before in a calculus course, because I made a question. You guys feel comfortable. But if you haven't, inflection point. So let's say potential inflection points over here with this condition. So potential inflection points are either the point 1 with 0.24 as y coordinate, or minus 1 with the same y coordinate. Now, the sign analysis will be actually pretty quick. So f prime of x is equal to minus x times e minus x squared over 2 divided by square root of 2 pi. And then, if you do the sign analysis, actually think about this as the factor. This exponential is always positive, so the sign depends on minus x. So f prime of x is greater than 0 for x less than 0. And f prime of x is less than 0 for x greater than 0, because the minus is changing the sign. And of course, f prime at 0 is equal to 0 by all the analysis that I did before. So the last piece of information, well, actually, we still have a couple, but the sign of f prime of x, if you think about it, now my domain is the whole real line. 0 is a critical point. F prime is greater than 0 for x less than 0. So if I consider the sign, here it's positive, here it's negative. So if I have f prime greater than 0, that means that the function is increasing. Yeah. if I have f prime less than 0, that means that the function is decreasing. So think about it. The function is increasing here and decreasing here. And here I have a local maximum at 0.4. So study it on your own. We will finish the exercise on last class. Good luck, and see you on Wednesday. Hey.
Question. When we're drawing these graphs, if we're doing this on a test, does it matter how we figure out what's curving up, curving down, where inflection points are, etc.?
Well, it depends because, look, one potential exercise is that you have a multiple choice exam, right? And you have 3 graphs, and somebody tells you for the function f of x equal to this, what is the actual shape of the function? And you can have like this parabola or this parabola, right? Or something different. So it might be useful to get used to this criteria. But